Okay, welcome back everybody. This is part 1 of lesson 8.6. I know it says 9.4, but this is 8.6. Today we will understand how to use the characteristics of a normal distribution to make estimates and probability predictions about the population, whatever population we're looking at. So you've heard me mention this in class, this concept of a normal distribution. What is a normal distribution? Well, it is a bell-shaped symmetrical distribution with a tail on each end. So let's put that out there. Bell-shaped, symmetrical, distribution with a tail on each end. With a tail on each end. Okay? And so that is going to allow us to understand. So when we talk about bell-shaped curve, we're talking about something that looks roughly like that. It's bell-shaped, symmetrical, or symmetrical as we can get it, and you can see these tails off on the ends. Okay? So we're going to use a graphing calculator. I want you to calculate the one variable statistics like we did a few days ago for the distribution of the data below. So that means I want you to take all of this data, put it into a list in the graphing calculator. You can put it into list 1 or list 2 or list 3. I don't care. It doesn't really matter where you put it as long as you put it in that list. And then go to stats, have it calculate the one variable statistics, and it should kick out these numbers. The mean, which is the x with the line over it. The mean for this data is 3.5. The median, which is the MED, is also 3.5. Here's a case where our mean and median are actually the same. Standard deviation, that is the sigma x symbol. Sigma is the Greek letter that we use for standard deviation, and it is 0.14. That is a small standard deviation, so that means most of this data is very close. And then the IQR, the interquartile range, is quartile 3 minus quartile 1, which in this case, quartile 3 is 3.6 minus quartile 1, which is 3.4. So our interquartile range is only 0.2. Okay? Now I also want you to take this exact same data and I'd like you to sketch a histogram of that data. Okay? Notice down here I've already given you the variable ranges. So 3.11 to 3.2, 0.21 to 0.3, so on and so forth. So we're going to have 1, 2, 3, 4, 5, 6, 7 different bars, and we would want to look at those. So how many numbers are in the 3.1 to 3.2 range? As I go back and I look over my data, there's only one number, 3.2. So I'm going to make that bar go up to 1. My next set of data, 3.21 to 3.3. There are, back up in my data, there's 1. And as I scan across, there we go, there's a second. So there are 2 that are in that range. Go up to 2. Down next, 3.31 to 3.4. Looks to me, let's see, 3.4, let's see, we've got 1, 2, 3, 4. Looks like there are 4 of those values. So we're going to go all the way up to 4. Bring that over. Next one is 3.41 to 3.5. Let's see how many of those we have. Coming back down, I've got 1, 2, 3, 4, 5, and 6. So on my histogram, the next one goes all the way up to 6. Okay, these are my frequencies. 3.5 to 3.6. Go back to my data. Got 1, 2, 3, and 4 again. So over here, I'm going to go up to 4. Make my line. All right, how about data that goes all the way up to 3.7? Back to my data. 1, 2. So it looks like there are just 2 of those values. And then for my last, up to 3.8, there's only 1. Okay? And there's my distribution. So then the question is, could this data be described by a normal distribution? The answer is yes. Why yes? Because it's bell-shaped. And it's symmetrical. Okay? Just because it's bell-shaped doesn't mean it's symmetrical. Bell-shaped is just that it has this shape, but that shape could be shifted one way or the other. Symmetrical is that it's pretty much down the middle of our distribution, so that makes it symmetrical. When we come back, we'll do video part